So far we have been talking about bound states as obtained by solving the Schrodinger equation. We are going to now change and talk about free particles, and in particular I am going to talk about free electrons, and when I say free electrons, that means the potential energy V is equal to 0, or equivalently V equals constant, and what that means is that the force on the particles is equal to 0, and therefore the Hamiltonian H, recall this, Hamiltonian is an operator for energy where H psi equals E psi, then H is going to be minus h cross square over 2 m d2 over dx square plus some constant potential which I have taken to be 0. So, this comes out to be minus h cross square over 2 m d2 by dx square in one dimension, and it is going to be h equals minus h cross square over 2 m del square, the Laplacian, plus v, which is minus h cross square over 2 m del square in 3D. So, we want to solve the Schrodinger equation for this particular Hamiltonian, and where is it useful? So, free electrons offer a reasonably good approximation to electrons in a metal, and I will talk about it more later. For the time being, the Hamiltonian in 1D is minus h cross square over 2 m d2 by dx square. So, let me focus on one dimension first, and therefore, the Schrodinger equation is minus h cross square over 2 m d2 psi over dx square equals E psi. That is my Schrodinger equation, and necessarily if V is 0, E is going to be greater than or equal to 0. This we have talked about earlier, and you have also seen this as a problem in the book. So, to solve this, what I am now going to do is write d2 psi over dx square is equal to minus 2 m E over h cross square psi, and therefore, psi double prime plus k square psi is equal to 0, where psi double prime is d2 psi over dx square and k square is 2 me over h cross square, which is greater than 0. So, the Schrodinger equation now comes out to be psi double prime plus k square psi equals 0, and the possible solutions are, you can check it easily, psi x equals e raised to I k x or sine k x or cosine k x or any linear combination. The question is, for free particles, which one is the correct solution? So, for free particles, which one of these solutions do we pick? That is the question. Do I pick e raised to I k x? Do I pick sin k x? Do I pick cosine k x? Remember, earlier when we were solving the Schrodinger equation, a particular form of the solution was decided by the boundary condition. So, recall that earlier the solution was picked by boundary condition. We are going to take some other consideration this time, and what we are going to do is first anticipate that in V equals constant case, the force is 0 and therefore, momentum of a particle is conserved. That means, what does it mean? It means that momentum does not change with time, and this happens classically. This is a classical result. Should we expect the same thing in quantum mechanics? So, the question I ask now is question: should we expect the same in quantum mechanics? Number 1, should we expect that momentum is conserved, and if it is conserved, what does it mean? Recall now, to answer these questions, that for stationary states, E, the energy, is conserved, right, or the matrix element psi I h psi j is diagonal in terms of Heisenberg's matrix mechanics. Recall that whenever there is a matrix which is diagonal, that means the corresponding quantity does not change with time and is conserved. So, here also if momentum is conserved, I should expect that psi I momentum operator psi j matrix will be diagonal. Right. So, this is diagonal. What that means is that if I write P matrix, it would have all off diagonal terms 0, there will be terms here which will be non-zero along the diagonal, and everything else would be 0. Now, the matrix for the Hamiltonian is also diagonal. Right. So, that means if I take the product P H matrix and subtract H P, this would be 0. Right. So, what that means is if a quantity is conserved, P H minus, or that corresponding operator satisfies, if a quantity is conserved, the corresponding operator, the corresponding operator O satisfies And let me write this on the next page. So, O satisfies that matrix of O times matrix of H, and if I change the order and subtract it, is 0. In the operator formalism, what it means is that O operator, H operator minus H operator, O operator would be 0. So, let me now state what I want to say. I turn the whole argument around and say if OH minus HO is 0, that means O would be a conserved quantity. So, if let us write it step by step, if OH minus HO for operator O is 0, O is a conserved quantity. And what does that mean? That means the wave function psi such that H psi equals E psi is also an eigenfunction of O. If it was not, so let us show this. If it was not, then psi I O psi j will also have diagonal elements. So, let us just summarize this by saying that if for an operator O, OH minus HO is 0, then H and O have the same eigenfunctions, and the quantity corresponding to O is conserved. And O is also referred to as O is also referred to as not O, but its eigenvalues are referred to as good quantum number. So, let us write it again, that H O minus OH is equal to 0 implies that H psi equals E psi, then gives psi such that O psi is also some O psi, and the eigenvalue of O is known as a good quantum number. Why? Because it is conserved, and the wave function psi is not only labeled by eigenvalue of energy E, but also the eigenvalue of that quantity O. With this background, let us now try to answer the question. Answer the question e raised to I k x, sin k x or cosine k x. Now, to anticipate the answer, again I go back to the classical result, that in the case when the potential is constant or potential is 0, momentum is conserved. So, let us now see if H p minus P h is 0. Remember what is P? P is h cross over I d by dx, And what is h? H is minus h cross square over 2 m d2 by dx square. So, H p would be minus h cross square over 2 m d3 by dx cube, the third derivative, and pH will also be h cross square over 2 m d3 over dx cubed, the third derivative, implying thereby that H p minus pH is 0. So, if I find that H p minus pH is 0, and by the way, when I write p here, this is the x component of the momentum, px. This means px is a good quantum number, px is conserved, and third, eigenfunction. When we say eigenfunctions, is a stationary state Schrodinger equation solutions are also momentum eigenstates. So, of the three, e raised to I k x, h cross over I d by dx of e raised to I k x gives me h cross k e raised to I k x. It is an eigenfunction of p. Sin k x gives me h cross over I d by dx of sin k x equals h cross k over I cosine k x, not an eigenfunction of p. Let us write as p x. And similarly, cosine k x is also not an eigenfunction. So, if I want to satisfy the symmetry property that the momentum is conserved, that p be a good quantum number and therefore, h and p have the same eigenfunction, the correct solution to pick is e raised to I k x. So, for free particles, this is the eigenfunction. So, for free particles with all the symmetry satisfied and all that, e raised to I k x is the eigenfunction. Notice that I have not written the normalization constant. So, normalization constant is yet to be determined, and also we want to find how to fix k. That means, is it continuous, does it change discontinuously, or what happens? Recall that for particle in a box problem, k was n pi over L. Here, how do we fix k? So, these two problems are related, and that is what we are going to address now. And the way it is addressed is through something called the periodic boundary condition. This is a trick through which we can count k's, we can enumerate k, and we can also fix the normalization constant. So, what periodic boundary condition does is demand that psi x plus L be same as psi x. That means, make the wave function periodic over a length L, and in the limit, thermodynamic limit, we let L go to infinity. What it means is L is very, very large. It is made so large that all the counting can be done through integration, and you will see in a minute. So, when we demand this, now psi x is equal to e raised to I k x, and this implies that psi x plus L is equal to e raised to I k x e raised to I k L, and this we want to be equal to e raised to I k x. And what this means is that we have e raised to I k L equals 1 or k equals 2 n pi over L, where n equals 0, plus minus 1, plus minus 2, and so on. This is how we fix the value of k, and when L goes to infinity, k changes almost continuously, or what I will call is quasi continuous. So, this is a trick of making k change continuously. I will be able to change the summation over k to integral over k, which I will show in a few minutes. And now, how do we normalize the wave function? So, the wave function is also normalized over this length L. So, what do we do is, suppose the wave function is taken to be C normalization e raised to I k x, what I am going to demand is mod psi x square integral from 0 to L dx be 1, and this immediately gives me mod C n square times L equals 1, or C n equals 1 over root L. And therefore, we are going to write the wave function psi x with periodic boundary conditions and box normalized over this length L as 1 over root L e raised to I k x. The moment I write this L here, that means I also imply periodic boundary condition over L, and this means k equals 0, 2 n pi over L, n equals 1, 2, 3 and so on, plus minus 1, plus minus 2 and so on. So, this is how we count k, and this is how we normalize the wave function. So, if I want to picturize this, suppose I draw it on a line, this is k equal to 0, every 2 pi over L there is one k value, 4 pi over L and so on. All these points show one particular k value on the negative side of k also. So, what I am going to say is every 2 pi over L there is a state psi which has energy h psi, which gives me h cross square k square over 2 m psi, and momentum p psi equals h cross k psi. So, it has a eigenstate of both the Hamiltonian and the momentum, with the eigenvalues being given here, and every 2 pi by L there is a state. Or this is also written in other words is that the density of states is L over 2 pi per k. You change k by unity and you get L over 2 pi states. If you include spin, then every state can accommodate 2 electrons. So, this is what we do in one dimension. What about 3 dimensions? So, next question we ask is, what about in 3D? the Hamiltonian in 3D is going to be minus h cross square over 2 m del square, which is minus h cross square over 2 m d2 by dx square. Now, I am going to change this d2 by dx by partial del 2 by del x square, because now I am going to have all three derivatives plus del 2 by del y square plus del 2 by del z square. We can do separation of variables and solve the problem. Now, again the Hamiltonian satisfies this equal to 0, because P vector, let me write this as a vector, is nothing but h cross over I times the gradient operator, and you can satisfy yourself that this satisfies H p minus P h equals 0, and therefore, P is conserved. One and the same thing, is a good quantum number, and therefore, the solution should be the eigenfunction of both h and p. And without going through details, I can just now tell you that psi as a function of x, y and z is nothing but e raised to I k dot r, which I am going to write that as e raised to I k 1 x plus k 2 y plus k 2 k 3 z. This is the wave function. There will be a constant in front, which we will discuss in a few moments, and h psi is now going to give me h cross square over 2 m k square, which is h cross square over 2 m k 1 square plus k 2 square plus k 3 square psi, which is the energy. So, this is the energy, h cross square k square over 2 m or p square over 2 m, and p psi is nothing but h cross k vector times psi, which is h cross k 1 x unit vector plus k 2 y unit vector plus k 3 z unit vector psi, and energy is p square over 2 m. So, in 3D this is what happens. Now, if I apply the periodic boundary conditions here, we get psi x plus L y z equals, I want psi x y z. Similarly, I want psi x y plus L z equals psi x y and z, and I want psi x y z plus L equals psi x y and z. And this immediately implies, just as it did in the case of one dimension, this implies that k 1 is 2 n, let me call it now n x pi over L, n x equals 0 plus minus 1 plus minus 2 and so on. Similarly, k 2 is going to be 2 n y pi over L, n y is 0 plus minus 1 plus minus 2 and so on, and k 3 is going to be 2 n z pi over L, and z is 0 plus minus 1 plus minus 2 and so on. And now, I am going to normalize the wave function over a cube of size L. So, I am going to have integration over the volume dx, dy, dz, Cn e raised to I k dot r mod square equals 1, and that gives me the volume L cubed times Cn square equals 1, or Cn equals 1 over square root of L cubed, which is also I can write as 1 over square root of V, and therefore, my wave functions now are going to be psi r is going to be 1 over square root of v e raised to I k dot r. This is the wave function in 3 dimensions with periodic boundary conditions and box normalized. Again, if I want to now represent this wave function in 3D, this is what I am going to do. This is my x axis or k x axis, this is my k y axis, and this is my k z axis, and by the way this is usually referred to as the k space. So, 0 k is going to be here. Again, every 2 pi by L there is one state on each axis. And then everywhere else, wherever there is an integer matching, there is going to be one state. So, these states are represented by these dots, where I just keep increasing everything by an integer. Let me make these dots on this side also. In other words, if I take this space and make a box of size 2 pi by L in the k space, there is one state in it. So, a volume of 8 pi cubed over L cubed, which is 8 pi cubed over V, has 1 k state, or we can say the density of k points in k space is V over 8 pi cubed. So, if I have some volume k space V k, if I multiply that by V over 8 pi cubed, I am going to get the number of k points in that k space volume. How about the number of electrons? Each of this k state can take 2 electrons each, 1 of spin up, 1 of spin down by Pauli exclusion principle. So, by now I have set up pretty much for you what all we require to do a very simple approximation for metals. So, let me conclude now this lecture by saying that for free particles, H equals minus h cross square over 2 m del square, then momentum P is a good quantum number. That means pH minus h, pH minus h p vectors is 0. The wave function psi x, y, z is 1 over square root of v e raised to I k dot r. V equals L cubed, I am box normalizing over a cube of L, and k vector equals 2 n x over L pi x direction plus 2 n y over L pi j direction plus 2 n z over L pi k direction. N x, n y and n z are all 0, plus minus 1, plus minus 2 and so on. And finally, the density of states in k space because k or p is a good quantum number. So, I can measure density in k space is V over 8 pi cubed per unit k space volume. With this, we will now apply these ideas to metals in a very simple way in the next lecture, where we will learn about Fermi energy, Fermi momentum and things like those.